Welcome to the 22nd, or the big Techday from 2022. And you probably all know what it is about, but it's our TNG Technology yearly big conference when we invite a lot of speakers we are interested into to have widen our looks into technology and the world around us. And so as you probably already know, we will be using Slacks for remote questions. And otherwise, people in the room can just raise their hands. That will work. And after the conference is over, for the seminars where we got the authorization, they will be posted on the Big Tech Day website, and they will be visible there. Okay. Now, let me introduce a bit Bart Markus. So he's a venture capitalist and entrepreneur. He has a background of applied physics and also an MBA, which helps with his current endeavors.
Physics helps more.
And after a start with McKinsey, he has been helping in the past 2 decades a lot of companies, from the startup size to successful IPOs or being bought by the likes of IBM, Nokia, Carl Zeiss, etc. At the moment, he's especially active as the CEO of Gap Technology Holding, and he has a bunch of companies under that umbrella, the most interesting of which are Ultimaker, you probably heard about already. Then Next Wave, which is using technology developed by the Fraunhofer Institute to advance solar panel efficiency and also lowering the price. Orbex, which is actually a space delivery company, which is
rockets.
Rocket company, basically. And they're specializing in delivering light satellites in an efficient and environmental friendly as much as possible way. And the one we are most interested about today, First Light Fusion, which has developed novel technology to advance nuclear fusion. So I will give you the word now, Bart.
Thank you. So we're not going to talk yet about basketball, but there is a purpose for this, and I'll get back to it about halfway through the presentation. So I'm Bart. The way I always describe myself that was a very long explanation. In one sentence, is I'm a geek turned business guy. So how many of you studied physics? Great. So I think we have a solid majority here. So that's good. I deliberately, obviously, it's a 40-minute talk about what we do at First Light. So it's not going to go into the depth, but I deliberately put in a bit more about what we do than I normally would, and that's why I have the basketball with me. And so I'm the chairman of the companies that you mentioned, also the chairman of First Light Fusion. First Light is the company that I probably spent most time with. Gap Technology Holding is just my family office. It's just it's a structure that it's me and my assistant. That's it. There's not more than that. So CEO of Gap doesn't sound. So why do we need fusion? I think that's why we need fusion, right? So I'm not going to get too much into that, but maybe there's an enormous amount of renewable energy being built today, but what we shouldn't forget is that today we use 27,000 terawatt hours of electricity per annum worldwide, and depending on who you believe, this is the most conservative estimate, we will in 2050 need 58,000 terawatt hours. The estimates go all the way up to 100,000 terawatt hours, right? So this is the most conservative. And then even if we would roll out renewables at the rates that people are forecasting, and by the way, we've missed these targets of rolling it out that way by a margin in the past 3-4 years, we still would end up with half of that roughly not being met. So we need a solution. Now, what people are starting to do, therefore, and I think Germany probably no escape, right? We have to go back to nuclear fission, atoomkraftwerken. And that would be one way to do it. But of course, as you all know, lots of problems with it. I mean, dangerous. It is a proliferation risk. And maybe most important, you have the nuclear waste. So fusion, if it would work, which it doesn't today, right, would provide a much better solution to solve, to fill that energy gap in a always-on electric power supply. So for the physicists, you remember this one? Okay, so if you think about, so you do fission, you take a 235 uranium typically, there's obviously different schemes, you fire a neutron at it, you split it, you get basically a Gaussian curve of all the isotopes below it, and a little bit of mass is being lost, and as a smart guy with my hairstyle many years ago already figured out, E is mc squared, a lot of energy comes out of that. Now, as you can see, per reaction, basically this is the binding energy, right, for the physicists here, the amount of energy per reaction is this bit, which already is huge. You do fusion, you do the opposite. You take two hydrogen isotopes, if you're sensible about it. You do deuterium, tritium. There is other fuel schemes, but they're all bonkers, frankly, to start with, right? Maybe in the end it's going to be different. You start here, you get two that come together, and you jump all the way up to helium, and per reaction you have that amount of energy, which is why fusion energy is so incredibly more powerful than fission energy is. There's per atomic reaction that takes place, there's, as you can see in the graph, a huge amount more energy coming out. Now, there's a challenge. So again, we take deuterium and tritium, so one proton, one neutron, one proton, two neutrons. You get them to merge together, to fuse, and out comes helium, which is, again, two protons, two neutrons, and the remaining neutron just disappears, right? And that has 80% of the energy in it, and you capture that energy. Now, the problem is that they're positively charged. So if you have a fission reaction, you take the uranium-235, it's neutral, a neutron goes in the right way, it will hit it, it will split the element, and off you go. So it's comparatively easy. If you take two positively charged elements, they don't want to fuse, right? So what you do is you need to get them to go at each other with enough speed that when they have the right point that they go at, they overcome the Coulomb energy until the strong force grabs them, and they fuse, right? So that is temperature, right? And the temperature you need is therefore is fuel dependent because it's entirely correlated to the Coulomb energy in there. And the Coulomb energy is trying to resist that. And for deuterium tritium, which is the most sensible, the easiest fuel to do it with, that's 150 million degrees, which is about 6 times the temperature of the core of the sun. So it's hot. But we can get there, and there's many schemes that get in these regions already today. Then the next thing is it's a probability. You need to have enough of these reactions happening. So there's really two elements that make that happen. You need a density, so you have enough of them in the same confined space moving at that speed, so you get the collision to happen, and you keep that as long as you possibly can. So it's a probability, right? And on that, so these three combined, if you Google that, it's a Lawson algorithm, it's a Lawson theorem, sorry. It's a triple product. It's literally these three multiplied with each other defines, whether you have a fusion reaction or you don't get a fusion reaction. It's as simple as that. Now, the temperature set is simply fuel dependent. The other two you can trade off. And there have been two main ways to think about fusion to date. Where the one is magnetic fusion, and it's basically ITER, which many of you will know, which actually is JET in Oxford, is the predecessor of that. Stellarator is the big German project, Wendelstein, which is a variation of that. Of course, as they're German, it's a more complex variation of a tokamak. I don't know if you've ever seen it, right? There's one at Max Planck here. You can go there. They love to show it. It's phenomenal. It's fascinating. It's crazy. But what you do is you actually have a plasma going around. It's a bit CERN-like, if you want, you confine the plasma in a magnetic field and you squeeze it. And then the fusion reaction happens. You add fuel, so it's like a furnace, right? It keeps on going all the time. That works. and it's proven a gain of 0.7. So 70% of the energy you put into the fuel is actually coming out of that in the world record, which actually is held by Jet in Oxford, in Culham. Now the other way, so you have a very, very long time for fusion that you can keep that, but you have very low density in there because you start at vacuum and you are near vacuum condition. So the pressure is lower than in the room where we are today. The other extreme is inertial fusion, and what you do is you squeeze a capsule of fuel very, very hard, so you get incredibly dense material, but that's it. After it's there, it will want to go out of itself, but there's inertia in there, so it takes time to get out, and now we're talking nanoseconds. So you have a couple of nanoseconds in which a reaction can happen. So the way that these guys get to the triple product is by having very low pressure, but very long time, a density, I should say. And the way that these guys get to fusion is that they have incredibly high, it's a miniature hydrogen bomb, frankly, a controlled hydrogen bomb. And so what you do is you have a very high density, but for an incredibly short amount of time. In both cases, you get to the triple product, and you get fusion to happen. Both have proven a Q of 70%. So, if we, and they've been going, those guys, 50, 60 years, those guys, 30 years, right? So, this is well understood, the physical. So why don't we have fusion power, right? Because we do understand we can do fusion, but we can't get there. Well, in the case of magnetic fusion, basically, in order to get the Q up, so to get more efficiency out, you need to make the machine bigger, 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 bigger. And at some point, I mean, I don't know who's looked at the videos of ITER, but it's crazy, right? I mean, it's a 4 football fields size machine hall. It's very, very, and for demo, which would be the power plant that I don't think will, well, I shouldn't say that, but that maybe will be built in the second half of this century. That is even, I think, 10 times the size of ITER or 5 times the size of ITER. I don't even know. In the laser side, the guys at Lawrence Livermore National Ignition Facility, they knew that they needed a bigger laser. They got a $4 billion budget to do the laser because lasers are at that energy intensity are very expensive, and so they couldn't put the laser in that they wanted, and that's why they got to a Q of 0.7, which is so they're basically on par, and the energy of the laser actually limits that. Now, on top of that, there's 3 major engineering challenges which people have, well, they've started to work on it, but haven't solved yet to get to a power plant. It is you need to, because you get, as I showed you the reaction earlier, you get neutrons coming out, and if the neutrons hit structural materials, they activate, depending on the material, but steel, they activate the steel, and you create low-grade radioactive waste, which it's not as bad as from fission, by far not as bad, but it's not what you want, right? So we need to solve. Also, the machine basically self-destructs over time, and that depends on what you do. But like Jet, I think it has the total lifespan of a fusion reaction is, I don't know exactly, but it's hours. It's not days. So they run the whole thing for whatever 20 minutes, and then 2 years later they run it again for 20 minutes, right? Or 5 years later. Then you need to manage the helium that comes out. That's a tokamak-specific problem, because you got this helium which you can guide out because they're, of course, positively charged, so you can actually manage where they go. And they go out through a thing which they call the diverter plate, because you want to keep your vacuum, to keep the plasma intact and stable. So you have this very tiny slit where you try to guide all these helium atoms through, but they're atoms, right? So some behave, some don't behave, and so they actually hit what they call the diverter plate. The diverter plate at Jet, and that's not a gain scale device, right, has the temperature 6 times the temperature of the space shuttle at re-entry, and that is a sacrificial piece on the space shuttle, right? The tiles are replaced for every time that they used to go up, and of course, I showed you the reaction is deuterium and tritium going in. Deuterium you can just get out of seawater, you can buy it, air liquide, harmless. I mean, literally you can go and buy deuterium. Tritium is a radioactive substance with a very short half-life, 12 years, and so it doesn't naturally occur. And so you need to generate it in the reaction. So you need to have lithium around there, and it needs to be hit by the neutrons, and then it generates in a different reaction, which we can spend another hour on, and it generates tritium. For having that efficient, you need to have a lot of lithium around it, but lithium is like a liquid metal at that point. So if you have magnets all the way around, you cannot have lithium in front of a magnet and the magnet still working, which I think that's pretty obvious, right? So difficult problems that they need to do, and they need to get to massive cost reduction. So this is where a number of new schemes come in to try to actually think about this in a different way. So leveraging on the work that has been done, but thinking about it different. Now we, at First Light, pursue a new approach to inertial fusion. Now, always you have this little cavity, it's a millimeter in size, roughly. Yeah, you can make them bigger, but then of course it becomes harder to control. Contains the amount of energy of a barrel of oil, and that goes back to the enormous power of the reaction that we talked about in the beginning. And then it needs to be imploded at about 100 kilometers a second. So as I also chair a rocket company, I mean, the escape velocity from where we are today to get to space is 10 kilometers a second. So it's 10 times the escape velocity of from where we are. And at NIF, which is the main inertia confined fusion program, they do that with a multi-beam laser. So they basically beam at this pellet from all sides, 192 lasers to be exact. What's a couple of lasers which then are split, and 192 beams that arrive at the target, and you get a spherical implosion, and you do that, right? And they're pretty good at that with the caveats that I mentioned. Now, what we do is we actually we take the same fuel pellet, as in literally the same fuel pellet, but then we choose at this point we choose a high velocity projectile, so literally a bullet that we fire at a target, and I forgot it. I always have one in my pocket. I would now hold it. So this is the imaginary target, but you look at the website and you'll see it there. That is a much cheaper system to do that, but still using the fundamental physics. And I'll come to, on the next slide, to how we exactly do that. The big difference between us and the other new startups that are doing that, so either they are going for a smarter way of doing the existing thing, like Commonwealth Fusion Systems, that's the guys in Boston that raised 1.8 billion last year. For a startup, not bad, right? I mean, I run a venture fund here in Europe, and we had $1 billion under management as a venture fund. This is one company that raised 1.8 billion. I thought, very impressive. Very good guys, by the way, come out of MIT. We really like them. They basically take a tokamak and they shrink it by using superconducting magnets. But of course, they don't solve the engineering challenges, right? And in fact, some of them become worse, right? Because if you have the heat flux, you need to get the neutrons out of a smaller machine, more heat flux, right? I mean, duh. Tokamak Energy's a similar scheme. The UKAEA, so Column, they're trying to do the same thing. Or people are doing very innovative and creative ideas, but they do then need their own physics. And then the problem is, I mean, of course, we understand a lot more. So if you come with a completely different scheme for the fundamental fusion physics, it took the MCF guys 60 years to get where they are today. It took the ICF guys, 30 years to where they are. And I'm hoping that it will take these guys only 4 or 5 years, indeed. But it's a risk, right? That they have. We work with the fundamental physics of NIF, and I'll come to the exact physics, but we deliver the energy in a different way. That's the. So what it does is we use for the reactor, because it's not just about solving the physics, about how do you get the reactor. So we take a projectile. Here you see the projectile assembly going in there. We then have a target that comes. That's the thing I have in my hand here, right? It is dropped in there. I don't know where it went. Okay, we drop it in the reactor vessel, and we fire the projectile after the target. It hits the target, and it makes the target implode, right? So that's a simple principle what we do. Now that allows us to have a liquid lithium, which is existing technology. So we basically borrow from fast breeder reactors, which use liquid sodium. And if you remember from your physics class, I mean, lithium, sodium right below each other in the periodic table, right? So very similar elements. And we are then able to capture all the neutrons in the liquid lithium, and it does a couple of things, right? And this is not something that, again, people have thought about this, but how do you do it? If you have a magnetic field, you can't, right? So we can do this because we don't have any magnetic fields. We have a standoff between where we fire the projectile through the tube and where the reaction actually happens. It captures the neutrons, so the neutrons don't reach the outer wall of the reactor, so we don't activate the reactor vessel. There is, of course, a shine path up, so we have we have a replacement part on the top, but that's easier to reach, so much less material that we'll be activating. So that's what we do. There's always a dirty little secret, right? In physics, as you guys know, there's nothing you get for free, right? So because this sounds, and in fact, most fusion technologies in the 70s have been thought of by some Russian guy, and it also projectile fusion. And the guy said, okay, if you want to do this, at gain skill, you need to fire the projectile at 340 kilometers a second, which again, that's about 30 times the escape velocity from the planet. You cannot fly a solid projectile on Earth, even in vacuum, at 340 kilometers a second, not possible. So that's where the basketball comes in. So what do? So the projectors are too slow. We are able today to launch at 20, 25 kilometers a second, which is incredibly fast already. Sandia Labs in the US fires projectiles at 45, 50. I think that's pretty much the max you can do in a scheme for a reactor. So nowhere near good enough. So what we need to do is and that's where our technology is. So we have the fuel pellet, right? The same one as that, exact same one that is used by the other guys, so we don't need to develop that. We literally it's published, right? We literally take that published design, and then what we do is we take a basketball, and we we have an amplifier where we take the velocity of the projectile, and we amplify that, or we converge that onto the fuel capture. So who remembers this experiment from physics? Ah, very good. This is good with this audience. So normally, the audience, I often talk to a bunch of financial people, and they've never heard of it, so they're totally surprised by it. So this is a ball, right? So it's for the lady from Allianz, from one of your customers. She will be surprised, hopefully, by this. And here is a small ball, right? Nothing special. I take both balls together, and I drop it. Exactly. And suddenly, the ball gets an amplification. So in this particular case, what it does, it's as you remember from physics, it's a transfer of momentum, right? From yeah, please. So excellent question. So we amplify today on our best amplifier designs. We amplify 12x.
Just like one step, or you do?
There's some secret sauce that we do not tell in the. So no, I mean, so. Yeah. So if you look at the website, at the First Light Fusion website, we actually, because we have recently demonstrated that this works and demonstrated fusion, validated by the UK Atomic Energy Authority. So thermonuclear neutrons coming out of that, we have also then published a number of our designs. So if we do a very simple, the first ones literally look like this, and you can, with material composition, we did I think it was I'm making this up now, but roughly a 2x, maybe 1.5x amplification. Then we have another one which has two big cavities and one small one, actually a tiny one. That's the one I normally have in my hand. We filed a patent on that 10 years ago. 10 years ago. And then the two big ones collapse. They create their own shock wave. They meet, amplitude goes up and hit that one. I think does an amplification of, again, I'm making it up, but it's give or take 2.5, 3x, yeah, maybe 4x, somewhere there. And that was 10 years ago. We do a lot more funky stuff than that today, right? So it's yeah. So that's what we. So basically, we create a convergence on the fuel capsule, and that's the core of our technology. So this bit, Los Alamos, that's the actual design we're borrowing today. But there's other ones that this one, Sandia Labs. This bit, a startup. Yeah. So don't try to do everything yourself. Now. Why can we do that as a startup? Because the key to any physics, hardcore physics development is always simulation. So if you want to get to that result, you will have to do many iterations. So for every shot that we fire, we have 3 platforms that we fire. So we probably fire about a shot a day. So for every shot that we do, I think it's on average 2,000 simulation runs. So we have a very large cluster ourselves, because that's where the secret source air-gapped from the world. And we do the simulation, we implement the physics in our models, and some of the simulation, we do an end-to-end simulation. I think it can run for 2-3 days on a cluster, which has, I don't even know how many cores it has, it's huge. It's not as big as Google, but it's very big. So here is, if you look at this, we talked about that, the triple product, right? Tokamak, that's where they are, right? So this is JET, these top numbers, the highest triple product. The laser guys, NIF, right? This is NIF, basically all of that. And then you see us, so, and you see just the speed of progression, right? It took them 60 years to get there, took these guys 30 years to get there, and this is us first slide. This, by the way, is Commonwealth Fusion Systems. So this is the last experiment that they did, and this is the one that we actually did earlier this year. So not just did in silico, but actually did the measurement that matched the silicon. And these ones are our newest simulation runs, which we trust will be right. But then, so we're getting to the same triple product in only, we've been around 10 years. It's still 10 years, right? Fusion is hard. So that's the big thing. You know, we've just shown fusion. First time that we did it with a single-sided impact drive. Today we use a projectile. There are other ways we could get the energy in. Again, that's not the core thing. The core thing is the amplifier. That's what we are able to do. So that's what we've done. So what are we going to do? So this, by the way, is you see the 2. You see and obviously, you know, the color coding shows the pressure profile. So the redder, the denser. I mean, so in the next stage, we will go and do a gain demonstrator, more out than in. That is a 7-year, our plan is 7 years, maybe 8-year program, right? So this is a machine that we fire on. So we use, in this case, we use a machine that is the same architecture as the Sandia Labs, the one that I mentioned, that fires at 45 kilometers a second. It'll have higher energy input than Sandia Labs. So they are doing 40 megajoules, and we think we're, you know, roughly 100 megajoules. So it's the same order of magnitude, right? Same voltage, that's important, so no inventions on switch or anything. The launch, again, we use the existing technology that we have developed there for launching the projectiles. So that's a plate fire launch that we do there. So we literally rip a piece of metal out of a, we call it the projectile assembly. This is, and then we use the Los Alamos revolver design. That is a well-known, published, that's the fuel pellet. So we didn't do that ourselves, right? This is what we do, right? Then, so we have to do these things too, but that's actually, this is the core of what we as a company do. Yeah, please.
Just for me to better understand the machine, what's the medium where this pressure wave propagates?
It depends on the target design. I'm sorry, but there's certain things that we keep proprietary on that. But we work with different. As this is being videoed, I don't want to get into this on the video what we use. We have many options that we can use as materials. But it's a. This is the
this is pressure inside the projectile.
Correct. No, inside the target. Inside the target. Yeah, this is why I'm stupid me that I didn't bring the target, but normally I would hold up and you would understand that it's a block about 1 inch on a side, and in there we have very funky geographies, and we use different materials, and that's how we create a pressure profile that converges onto the what did I call it? Fuel capsule. Thank you. Okay. Business, as I say, I'm a geek turned business guy. So in the end of the day, the power plant, everything around it is existing, by and large, existing technology. Obviously, will need to be adapted. So we then will supply the fuel pellets to the people that will operate these power plants. So pick your analogy. I happen to like Nespresso capsules, but printer toner, what have you. So we have, that gives us the ability, because it's not just about solving the physics. It's not even about building the first plant. It's about, if we are going to fill that, 40,000 terawatt hour gap with fusion, that is thousands of plants, right? So we need thousands of plants. So if you have one startup, can't build even one big power plant, right? So we will work with other people. So we'll be building, at least we think we'll be building, plants in Japan with Mitsubishi, which have done these fast breeder reactors, in France with EDF, which has done fast breeder reactors, in the US with Bechtel. So we can scale our business, and that's good for the business, but it's of course also good if we want to actually make a contribution to climate change. So we take 20%. Flip side of that is we leave 80% on the table for the people that build power plants today. So instead of fighting the system to try to build nuclear fission power plants, we tell these guys, okay, you know what? We change so we need deuterium and lithium. We create what we call the fuel, right? The targets out of that. So we'll manufacture them, and then everyone else keeps on doing what they do today. That's the plan how we do that. So that means that this is in the long term a core business. Of course, in the beginning when we do the reactor design, there's a lot of these special things that we need to be involved and help them to make it, right? So short term, we will have to help these guys to do that. And we're starting these discussions with these people today. So that means there's another thing. It's like if you want to start a fusion power plant, you need to put deuterium and tritium in there if you want to have a decent output. There is no tritium in the world, right? It's a controlled substance. It's also, you can only generate it in a nuclear fission plant today. In the Western world, there's one plant in Canada that does that. And so that means that there's a need for, it's actually the stuff that if you have a higher end watch that glows in the dark, right? That's actually tritium that you have on there. Or tiny fractions, right? I mean, so that's what we use it for. It's used for in medicine. It's used, actually they used to use it, I don't think they do anymore, for cinema science exit. What the glow in the dark stuff is actually tritium. It's radioactive. But you shouldn't make jokes like that. Sorry, and that means that if all these other guys really struggle to make tritium or to generate tritium for themselves, so they will have to, like Commonwealth Fusion Systems, which I think will also have a power plant on the grid, for them to actually start that up will take them a long time before they can go from DD, where you start, generate a little bit of tritium so they can feed the tritium back into the plant. We can actually supply them with, okay, you want to start your plant? Here's the tritium, right? So we can generate twice the tritium that we need simply because we have the lithium all the way around the reaction, which they can't do. Yeah. So there's a way for us to get a commercial plant or the first pilot plant actually profitable from the very first moment. So who do we do this with? The founder is Nick Hawker. We're spin out from Oxford University. He did his PhD there on, actually it was on a thing called the pistol shrimp. So it's a little creature that lives in the very deep ocean, and it has a huge claw, and it actually snaps its claw and then does that with such a force that it generates little bubbles that implode and create a plasma. And then it stuns its prey, and it just walks over there and eats the prey. So that was what his PhD was on. I said, well, can we use this for something, useful? And that's where it all started with. Very experienced team. I mean, Gianluca, CEO, was the chief engineer at Formula 1 and 2 teams. CFO of many startups, actually, Dave. Paul, that was at Rutherford, built the big laser that they have there. That was him doing that. And of course, we have a Nobel Prize guy on the scientific advisory board. That would be Steve Chu. This guy here, Dick Garwin, is the guy that there's a book written about him, and it's called True Genius. And apparently Fermi, which he worked with, said of Dick Garwin, he's the only true genius that I've ever met in my life. And so he actually created the first hydrogen bomb for the US, so made it work. So the inventor, of course, is Teller, but he's the one that actually got it to work. And he's 90. I think now 95, but he still is actively involved in the company. Arun was the first CEO of ARPA-E, the Advanced Research Project Energy in the US, and he just got nominated the chair of the John Doerr, the new $1 billion Stanford sustainability thing. So lots of people that actually know what they're doing there. History, I think, so we came out of Oxford. We used the first 5 years to show plasma. I say we, I wasn't there. I've only been involved with the company for 5 years now. So I came in, I guess that makes it 2017. Then we did fusion. So we just demonstrated that earlier this year. And we've raised $100 million, 77 million pounds to date, which in fusion terms is small money. We work with an ecosystem of many of the research institutes, national labs, because we do not think we can solve this whole thing by ourselves. The thing we do solve ourselves is the amplifier. That's us. All the other things we try to borrow, try to work with other people. And so we're very open in our collaboration. So we've come out with, that's why we've published papers. For the geeks under you, there's lots of papers on the website that you can download to figure out how it really works in depth, in a depth that I don't know how it works, right? So that means that where are we in our journey? So we've just demonstrated fusion. Next phase will be to show gain, right? And in parallel, we'll try to get to a detailed design point for a power plant, which then, and of course depends on the appetite of people, the risk appetite of when will they start to actually break ground, and do they want to get a bit ahead of it, or do they want to wait until there? So in the early 30s, at some point, we should have that first pilot plant on the grid. And our goal would actually be to have 2 of those. So one in the UK, obviously, but one somewhere else. So that's our plan. So for that, we're actually just starting to raise 430 million pounds, so it's $500 million, which we literally are kicking that process off. We had a board meeting 2 days ago where we decided to go, and that will be for the gain demonstrator, the plant engineering, and also build the commercial operations to build these partnerships. So I think that is what I had to say in form of presentation, and then I think we have some time for questions, right? I think I'm on the dot, am I not? 9:40 you said, it's 9:38.
That was perfect. Thanks.
Questions?
So just as a reminder, we will be taking questions from the room and from Slack, so not from other remote sources.
How much do you need? Sorry. So lithium is limited on the planet. How
Yeah.
much lithium do you need? Is that a problem
Excellent question.
for scaling up?
I get that. So I don't actually have the number at hand, but the amount of lithium we consume is tiny. It's kilos a year for a gigawatt power plant. So it's nothing because the reaction is so incredibly efficient. However, we do have in the power plant, we have a large volume of liquid lithium that's moving around. So it's not actually what we consume. It's more filling up the plant with lithium in the beginning. But it's hundreds of tons of lithium, which compared to what we use in battery production, it's a tiny fraction, even if we do the full 30,000 terawatt hours a year. And I'm sorry, I should probably have that number at my fingertips, but I don't. But what the exact number is, but it's a tiny fraction. Also, we can, of course, as we do something with the lithium that's much more value add or value generating than a battery by kilo of lithium, we can pay much more. The lithium is not, it doesn't factor in, it doesn't appear in the LCOE. It's not like out of the $45 a kilowatt hour, it's not $1, it's much less than that. It doesn't appear. So it's not a problem, but it's a good question. Yes?
So two-part question. One, did I understand this correctly, that once a plant is operational, it actually produces all the tritium that you need? And what would roughly be the cost of actually manufacturing such a targeted piece? Because that's a consumable, right? The entire battery.
Yeah, so the question was like, will the plant produce its own tritium, and what is the cost of making the target? So Yes, and this again, it's a good question because on all the other schemes, not all, but on the main, like in particular the tokamak, the main MCF, it's not obvious to generate that the tritium yourself. So actually, what they do is they take the lithium. So we will use, I should say, because we don't do a tritium cycle yet, right? I mean, we don't need to. We fire one target, we just literally buy the tritium, right? But today, in a tokamak power plant. They cannot use the natural isotope mix of lithium. So they actually need to enrich it. So they shift it more to lithium-7, I think. And then that's not enough with the volume they can cover. So then they start to do funky reactions. So they start to add stuff in there like beryllium and stuff. And then you get intermediate reactions. And, well, you get the stuff that you would expect when you add beryllium in there. Not all pretty. And so that's a real challenge. We can use the natural isotope mix. And because we have, I think it's 96% of the circumference we have lithium. It's only the bit where we drop the projectile and fire that's not covered. And so we can actually generate, call it twice. I mean, the amount of tritium that we would need, and we tune that by the thickness of the blanket. So if we make the blanket thicker, we generate more tritium. Make the blanket thinner, we generate less tritium. So that's the cost of the target is not something we're working on today. Obviously, I mean, it's kind of like a little bit of a challenge, right? So when you have a big problem, you cut it up in small pieces and you do them one by one, right? I'm sure you guys do the same thing, right? You write a bit of software code, you don't start with all, 4,000 lines of code at once, right? You start with a module and you add another module and then you put it all together, right? I mean, at least that's how I did it when I was doing coding in the 80s. In the 80s, can you believe that? So different coding in those days. What I will refer to is Lawrence Livermore, because they thought about that long and hard. So there's a couple of papers you can just download from the Lawrence Livermore website. And the targets they fire, because they are really trying to get to QS1, right? So they save no cost on targets. They cost $1 million a target. And they have a paper where they then look at the manufacturability. They want to fire at a rep rate. I think their design point is 10 hertz. 10 targets a second. Our design point is once every 30 seconds. So and that's because we can use a bigger target and blah, 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 blah. A lot of reasons for that. They think that they, at volume production, they can get, because you make them in a totally different way when you make, in their case, God knows, 300 million a year, I guess, right? So at 10 hertz. So they think they can get to below $1. A target from $1 million. So I don't think you should, anyone who's done physics experiments knows that if you put an experiment up, the cost of the experiment and the cost of the industrially manufactured mass-produced solution are very different. So we will work with a target projectile assembly plus target cost, of give or take $30 at our design point. So we think we can do that, but we've done some broad analysis of, okay, do we think we can get there, but we need to use mass manufacturing technologies. Yeah, there was one question there, no?
Yes, it was a similar question. You talked a lot about the design of the target in the amplifier, and I was wondering if you foresee any major roadblocks in the mass production since they're consumable.
There will for sure be really big engineering challenges.
Can you repeat the question?
Oh, sorry. So do we foresee any roadblocks in manufacturing these targets? As you say, a related question. So for sure, there's going to be huge engineering challenges to do that. But there's people that can do that very well. If you look at the obvious example, whether you take the Nespresso capsule or your razor blade, they are made at cents. It's not an easy production process either, right? What do you know what trick question. Do you know what the tolerance is on a Lego block? I met the CTO of Lego the other week, and he told me, I was blown away. Any guess? I need one guess before I give you the number. Sorry? Yeah, it's 3 micron. So, and that's the kind of tolerances that we believe that we will be needing to. Probably more like 1, but if Lego can make Lego blocks for 3 at a tolerance of 3 micron, can we make this stuff at a tolerance of 1 micron. It's going to be hard. I mean, but there's harder things we're solving now. I mean, so, yeah. Okay. Sorry. Yeah. Anything in Slack?
So
you want to give your Slack colleagues? No.
okay, so
All shy.
you're concentrating on getting more power out of the fusion step than you put in, but there's power being consumed in the whole value chain.
That is correct.
So what's the
Okay,
let's say the rate? What's the fraction?
As it's a technical, so the question was, and again, excellent question. So we are focusing on getting more power out of the fuel than in. So when we talk about gain, like everyone, by the way, we talk about gain at the fuel level. But if you want to have a power plant, you need to have what people call wall plug gain. You need to take the whole chain into account. True. In ICF, there's a thing that's called fuel burn, so ignition. So when actually you get that bit of fuel that you have there starts to react, that it starts to self-heat, and it actually then propagates through the fuel. And then you can start to do interesting stuff like NIF, for instance, they work with hot fuel and cold fuel fraction. So they freeze part of the fuel, so it doesn't get ignited. Then they get self-ignition, and you get, so when you get target gain or fuel gain, that also means you get ignition. When you have ignition in further target designs, relatively, and they're there again, right? We wouldn't reuse other people's stuff again. So you can get to a propagating burn, and you can get to more energy by doing that. So that's the answer in there. So the first, it's one step at a time. So we did fusion. Next step, fuel gain. Next step, different targets that actually allow you to, and once you go in ICF, that's an ICF thing, it's not an MCF thing. People always compare the two together, even on triple product, frankly, it's not a perfect comparison, but as the MCF guys were there earlier, they made that the thing that everyone compares on, so we map, as NIF does, ourselves on that map too, but it's not a perfect comparison. If you get to fuel burn in ICF, it actually becomes asymptotic. So when you get to that point, you actually can get, so it's not like, oh, can we get 5 times? Can we get, no, you can get 100, you can get 1,000. It's, that's actually, it's a bit like the manufacturing question. So it's comparatively, it's a smaller step, but it is a step. So when we have gain, are we done? No. We'll need to get to, high gain, as we call it, and we'll need to get to manufacturability of the targets, and we need to get our partners to build power plants, where they need to adapt the liquid sodium to the liquid lithium. So it's kind of like, it's a challenge, stuff that we need to do.
So there's one question from Slack. How do you imagine a world with large-scale deployment of fusion energy? Does it look very different from our current one?
Yes. Yes. This is my favorite question, because as I say, even though I'm a geek turned business guy, and this is on the business side of things, I think if we have a source of energy that is clean and basically without limitations at a reasonable cost point, we can, you want to reforest the Sahara? Sure. Let's boil the Mediterranean. Why not? We can do that if we want to. Today we can't do that, because if we want to reforest Sahara, we can actually. By the way, I was in the Middle East 2 weeks ago, and they boil. I was in Doha. They boil the sea to provide all the water that city uses. They do it today, but they burn oil for it. So you can reforest the Sahara by burning oil. That's not a good way to do it, right? So I think we're going to have a very different world. So these 60,000 terawatt hours in 2050, that's based on our current knowledge of where the world is. If we have this source, I think we're going to have a lot more power consumption than that, because we can do phenomenal things with it, which we haven't even thought about. And me saying, let's reforest the Sahara is just one of them. I think, by the way, we should reforest the Sahara.
Hello, I have a question regarding your motivation in climate change. let's assume a scenario where we met the climate targets, 1.5 degree or 2 degree, and keep below that.
You mean with Holland or without Holland? 2 degrees would be without Holland. I'm from Holland, right? 1.5 would be with Holland. I'm just joking, so please continue.
So my question is, how much will fusion energy attribute to meeting the targets? Because 2030 seems early for fusion energy, but it seems late for climate protection.
Yeah, so the question was, aren't we too late? That's a simple way of putting the question. Is this not too late? Frankly, yes, we will be relatively late to the party. But, is there a too late? I don't think there is a too late. I hope there's not a too late. There's also, it's a matter of how willing are we to actually throw money at this? Because we talk a nice story about meeting climate. I was saying in the very beginning, right? We say, okay, here's our projected deployment of renewables, and then we use a system to do that, which is driven by energy prices, by capitalistic system. Then we go into, we get an energy crisis. We don't have gas from Russia, and the layer guys are turning back on the coal plants, right? I mean, to make sure that we don't get cold this winter in Germany. So I think as humanity, this is on video, right? So can I say that as humanity, I think we're pretty much fucked. But it is, I think we just need to do it. And if we throw more money, if we would throw more money, and by the way, there's a lot of money going into fusion. But on the chart I showed you, we now do everything sequential, which is, the right way to do a startup. But if you think this is a real problem, if you want to have fusion earlier, well, let's build this plant today. And then if we don't get there with the technology, you know what? The plant will cost, I think, 600 million, 700 million, the pilot plant. We will have wasted 600 million. We could be there 10 years earlier. But, we are talking to governments, because this will be a government thing, right? We are talking to governments about that. But, and then the election cycle comes and, Boris jumps out of the window, or he doesn't actually, and, it all becomes, problematic. I mean, Draghi tries to resign. Draghi, right? I got it right this time. I said Monte earlier, that was not good. Yeah. Okay, so, we can do this faster. But there's no magic. I mean, we cannot do this you got what we're trying to do, right? I mean, we can't do this in 2 years. I mean, that's not possible. But can we have the first power plant on the grid instead of in the early 30s, in the late 20s? Sure, if we take more risk, if we could. And then it may not work. And then we need to build another one. Yeah, sure. That would be a way. Yes?
Maybe a follow-up question. Should I get the microphone?
No, you just talk, I'll repeat.
A follow-up.
You do the long version, I do the short version.
Yeah. You talked about funding and risk and going there in 2 years or not. It seems that you are a very European-based company, and as I believe China is the biggest player on fusion technology and research nowadays. So wouldn't it be very quick or even more capital there or venture capital in China if you would say, okay, Europe sucks if it comes to energy. Let's go to China because they have the biggest energy problem in the world and they are inclined to solve it the fastest, and you might be able to just get the money to fit your.
Yeah. So the question is. Yeah, I get the question. So the question was, should I move to Beijing? So should we be in China instead of in? So we definitely are a European company. The center of fusion intelligence is Oxford today, no question. I mean, it's where JET is. It's where got the General Fusion guys out of Vancouver. They're moving to Oxford. I mean, we're there. The UK has always put a lot of money there. So the center of true research is Oxford. The stuff that the Chinese are doing east is the obvious example. Is decades behind what JET is doing. Now, do I believe that if we roll out fusion technology and power plants, so where China is ahead of everyone else, is the rollout of nuclear fission power plants. They're actually the only ones that are rolling out nuclear power plant, and the Russians a little bit at scale. So do I personally believe that abstracted, and I'm not a politician, right? So abstracted from politics, do I believe that China should be the country where we roll this technology out en masse? Absolutely. And will they do it quicker than anyone else? Absolutely. Will we be allowed to do that by the politicians? You tell me. Yeah. But the thought didn't escape our mind. And by the way, our collaborations are not just European-centric. Actually, we've got quite some cooperations, because Europe has for a long time focused on MCF, magnetically confined fusion, the Tokamak variants, and the US were the ones that jumped on the ICF bandwagon. So our main collaborations with national labs are actually Lawrence Livermore and Sandia Labs, which is really where the ICF community is. And actually many of the people, but some of the people in our company come from there. Yeah.
Okay, sorry, but we ran out of time for the questions. And let's thank Bart for the very interesting talk.
Good. So, thanks for listening. I'm going to grab a coffee at the bar. So if you want to have a chat, you have to. So I'm just going to introduce a 8th stream, which will be chat to Bart at the coffee bar, if you don't want any of the other presentations now. Thank you guys very much for listening.